This is a video key for the review for Module 2 assessment. So for the first part, for 1 through 9, we're looking at learning target 9. I can use integer exponent rules to simplify expressions. So for number 1, we're looking at a product of powers. So remember, when we multiply two powers with the same base, we add the exponents. So we're really doing 2 to the 4 plus 7, or 2 to the 11th. For problem number 2, we have 9 to the 0 power, and by our 0 power rule, remember that anything to the 0 power except 0 is equal to 1. For number 3, we have a quotient, so we have the same base. So when we divide two powers of the same base, we subtract the exponents because they cancel each other out. So we're really doing 8 to the 20 minus 5, which is 8 to the 15th. And if you're unsure how to do any of these, you can always do them in expanded form, which is how we discovered the rules. But remembering the rules helps you go through them a lot faster. All right, for the next one, we have a power to a power. So the power rule says when you take a power to a power, you multiply the exponents, because we're going to have 5 to the third 7 times. So we'll have 5 to the third times 5 to the third, etc. And so that means you'll have 5 to the third 7 times, which is a total of 21 5s being multiplied. So 5 to the 21st power. For number 5, we have our negative exponents. So remember that a negative exponent means we're actually dividing by the base that many times. So if we want to divide by 7 9 times, we got to do 1 divided by 7 9 times. So 1 over 7 to the 9th. Number 6 is just like number 4. So we're taking a power to power, we multiply the exponents. So it's really 10 to the 8 times 4, or 10 to the 32nd power. Number 7 is just like number 3, where you have a quotient of powers. So when you divide two powers with the same base, you subtract the exponents. So that's our quotient rule. So it's 14 to the 7 minus 6, or just 14. You can put to the first, but you don't have to. Number 8 actually combines two different rules, so you got a couple things going on. Let's go ahead and look at the numerator first. So remember that when we just have a factor by itself, it's really that factor to the first power, so 4 to the first, times 4 to the 8th uses the product rule. When you multiply two powers with the same base, you add those exponents. So it'll be 4 to the 1 plus 8, which is 4 to the 9th. So I'm going to go ahead and write 4 to the 9th over, we haven't done anything to the denominator yet, so 4 to the 3rd. Now we use the quotient rule. So when you divide two powers with the same base, you subtract the exponents. So 4 to the 9 minus 3, or 4 to the 6th. And that will be your final answer, 4 to the 6th. For number 9, we have 3 to the 5th to the 2nd divided by 3 to the 7th. So again, we've got a couple things going on here. So in the numerator, 3 to the 5 to the 2nd is taking a power to a power. So we, just like number 4 and number 6, we multiply those exponents. So that'd be 3 to the 5 times 2, or 3 to the 10th. So I'm going to write 3 to the 10th over 3 to the 7th, because we haven't done anything with the denominator yet. And then that equals, we use the quotient rule, so that's 3 to the 10 minus 7. You subtract, when you divide two powers with the same base, you subtract their exponents. So that would be a final answer of 3 to the 3rd. Now notice here, we could not have done this in a different order. For this one, we could have. We could have used the quotient rule here and got 4 to the 5th, and then 4 to the 5th times 4 to the 1st would have been 4 to the 6th. But for this one, since this is in parentheses, we have to do this part first. Since a power to a power will always come first, because we do what's inside the parentheses first, and powers first before we do division. So you would have had to have done that one first. For number 10, what are the requirements for a number to be in scientific notation? Well, the front number, or the factor, must be between 1 and 10, not including 10, and it must be multiplied by a power of 10. So it's going to be something times 10 to the something. So it's got to be a product of some number between 1 and 10 and a power of 10. Next part is learning target 11. I can write numbers in scientific notation. So we are going from standard notation to scientific notation. So when you do these problems, remember you should first identify whether the number is big or small. So this first number is big, and the reason we do that is because the big numbers will always have a positive exponent because you're multiplying by 10 and making that number bigger. And small numbers will always have a negative exponent because that means you're dividing by 10, which means you're making the number smaller. So since this is a big number, here's my decimal point. Since it's a whole number, it's all the way to the right. We count how many times it takes to make this number between 1 and 10 by moving the decimal. And remember, when we move the decimal, we're actually dividing by 10. So 1, 2, 3. So if I move it 3 times, I get the decimal 5.26, and you don't need the 0 since it's the last number. When you're writing in scientific notation, you don't need that. But you do need the 2 digits that are non-zeros, or any non-zero digit you do need to write. Times 10 to the, since I divided by 10 1, 2, 3 times, I need to turn around and multiply by 10 3 times so that the number is still equal. So these are equal. And again, to test whether you're right or not, you can take this and turn around and put it back in standard notation and make sure you get the right answer. For number 12, we can see that this one is a small number. So we're going to move that decimal to the right because we need to make it bigger to make it between 1 and 10 to be in scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I move it 10 times, I get 8.9 times 10 to the, since I moved it to the right, I multiply by 10, but it's actually very small, so I need to turn around and divide by 10 times. So that gives us a negative exponent. And again, it matches small number, negative exponent. And again, we can take this our answer, put it back in standard notation and make sure that we got the same answer. Number 13 is another big number. So we're going to take that decimal and actually divide by 10 to get it between 1 and 10. Again, it's all the way to the right since it's a whole number. 1, 2, 3, 4, 5, 6. So I moved it 6 times. And again, I need the 0 and the 8 because the 8's non-zero. I need any digits that are 0 that are between non-zero digits, and the rest of the zeros don't have to be written. Times 10 to that, I just divided by 10, 1, 2, 3, 4, 5, 6 times. So I need to turn around and multiply by 10 6 times to make the numbers equal. So it matches. Big number, positive exponent. Number 14 is a small number. So we are going to take that, that decimal place, move it to the right. 1, 2, 3, 4 times. We move it 4 times, we get the decimal 3.12, which is in between 1 and 10. Times 10 to the, since it's a small number, or my exponent's negative, because I moved it to the right, multiplied by 10, so I have to turn around and divide by 10, otherwise the number is not equal. I moved it 1, 2, 3, 4 times, so it would be 3.12 times 10 to the negative 4th. So the next learning target is going the other way. So learning target 10, I can convert numbers written in scientific notation to standard notation. So the same idea goes when you have a positive exponent, that's a big number, and when you have a negative exponent, that's a small number. So what you should do is rewrite your given number. And so I know that's a negative exponent, so I'm going to be having a small number, so I'm going to move it to the left because that's dividing by 0. So I'm going to write my number off to the right because I know I'm going to need decimals here off to the left. So I'm going to move that decimal 1, 2, 3, 4, 5, 6 times. And go ahead when you do that, make a big decimal point, and that's your new decimal point, and fill in with zeros. So this is your new decimal point. This is the old decimal point. So this is no longer there. And rewrite your final answer. So my decimal point and now you can count zeros. 1, 2, 3, 4, 5. So I got to put 5 zeros to the right of the decimal. Then 8, 9, and then you can add that 0 to the left of the decimal, but it does not count for one of these zeros. So that's your answer in standard notation for number 15. Negative exponent, small number. Number 16, we have a positive exponent, so I know I'm going to have a big number. So I'm going to write my decimal over here because I know I'm going to have to put a lot of zeros and decimals over here, or move the decimal over here. So I'm going to move it 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, put a big decimal. That's your new decimal place. That's a new spot, so it should not be written here anymore. And we fill in with zeros. Okay? So I don't have to put anything after the decimal since this is a whole number. So I'm going to count my zeros so I can keep track. 1, 2, 3, 4, 5, 6, 7 zeros after 302. 302, 1, 2, 3, 4, 5, 6, 7. Now we go back and put commas every 3 numbers starting from the right to the left. So 1, 2, 3, here goes a comma. 1, 2, 3, here goes a comma. And 1, 2, 3 is the last comma. So that's 3 billion, 20 million. And again, it matches positive exponent, big number. Number 17 is a positive exponent, so this will also be a big number. So I'm going to write my number here and get ready to move my decimal place 4 times. 1, 2, 3, 4. Big decimal point because that's the new decimal. It's no longer here because I'm multiplying by 10. Put in the decimal, so I got 65 and then 3 zeros. Every third number you put a comma starting from right to left. We don't have to write the decimal because it's a whole number, so it's just 65,000. Big number, positive exponent. Next one, number 18, we've got -2, we've got a negative exponent, so this is going to be a small number. So I'm going to write my number over here and get ready to move it. 1, 2 times. Put a big decimal point because that's your new decimal. It's no longer here because I divided by 10 twice. Fill in with a 0. So I have decimal 0, 1, 2, 3. And again, you can put a 0 to the left. And again, my final answer matches negative exponent, small number. On the back side of that front page, we are now going on to learning target 12. I can perform operations with numbers written in scientific notation. So we are going to do these operations. Remember, when you add and subtract, just like fractions, you have to have a common power. Just like fractions need a common denominator. For multiplication and division, we do not need to have a common power. Just like when we multiply fractions, you do not have to have a common denominator. So for number 19, we are adding, so be aware of that. That means we need a common power. So the easiest way to do this is to change the smaller power to a bigger power. So I'm going to change this to a 4, and because I increased that exponent, I made that number bigger, so I need to turn around and make this number smaller. So I'm going to move the decimal to the left one. So now we're looking at 0.32 times 10 to the 4th, which is the same thing as 3.2 times 10 to only the 3rd. But now, since they have a common power, I can add their factors. So I'm going to come over here and add 9.8, and you have to line up the decimals. 9.8 plus 0.32, I'm going to fill in with a 0 here. We're going to add, so 0 plus 2 is 2. 8 plus 3 is 11, carry the 1, and then 9 plus 1 plus 0 is 10, so 10.12. So our answer is 10.12 times 10 to the 4th. However, while that's an answer, it's just not in scientific notation because this number ended up being bigger than 10, so I need to adjust it. So I'm going to take the decimal and move it to the left. So since I made that number smaller, I have to turn around and make this bigger so that the number's still equal. So 10.12 times 10 to the 4th is the same thing as 1.012, keep all those digits, times 10 to the 5th. And that is your final answer. Number 20, we're subtracting, so we also need a common power. So again, making the smaller one bigger is easier. So I'm going to change this to a 12. Since I made that bigger than it's supposed to be, I need to turn around and take this number and make it smaller. So I'm going to move the decimal to the left. So now it's 0.21 times 10 to the 12th. So remember that these are the same number. 2.1 times 10 to the 11th is the same thing as 0.21 times 10 to the 12th. Starting here and going to the right 11 times is the same thing as starting one back and going to the right 12 times when you're looking at putting it in standard notation. So now that they have a common power, I can subtract their exponents or their factors. So since I'm subtracting, I know I'm subtracting because that's the operation it says. So just be careful on paying attention to whether or not you're subtracting or adding. So I'm going to subtract 5.4 minus 0.21, and again, you have to line up the decimals. Fill in a 0 there, subtract. I'm going to have to borrow, so I'm going to borrow from the 4, make this 10. 10 minus 1 is 9. 3 minus 2 is 1, and 5 minus 0 is 5. So I get 5.19, which is between 0 and 10, or 1 and 10, so I'm going to go ahead and put this in my final answer spot. So 5.19 times 10 to the 12th. You keep that common power. And that is your final answer for number 20. For number 21, we are doing multiplication now. So this is a little easier because we don't have to get a common power. So all I'm going to do is rearrange the numbers. Since it's all multiplication, I can do it in any order that I want. So I'm going to do 3.4 times 4.7 times 10 to the 5th times 10 to the 9th. And I do that because it's really easy to multiply those powers of 10. It's 10 to the 14th because when you multiply two powers with the same base, you add the exponents. Then I'm going to come over here and multiply 3.4 times 4.7. 4 times 7 is 28, carry the 2. 3 times 7 is 21, plus 2 is 23. Bring a 0 down. 4 times 4 is 16, carry the 1. 4 times 3 is 12, plus 1 is 13. And then you add 8 plus 0 is 8, 3 plus 6 is 9, 2 plus 3 is 5, and 1 plus 0 is 1. Now for the decimal point, I have 2 digits to the right of the decimal. So down here, it's 2 digits to the right of the decimal. So I get 15.98 times 10 to the 14th. Again, that's the answer, but it's not in scientific notation, so we do want to adjust it. So we need to move this decimal to the left one to make it between 1 and 10. So since I made that number smaller, I need to turn around and make this number bigger. So 15.98 times 10 to the 14th is the same thing as 1.598 times 10 to the 15th. That's your final answer for number 21. Number 22, we're dividing, so it's just as easy as multiplying. So I'm going to rewrite that as two separate fractions. So kind of like we did with multiplication, we can kind of reorder it. So we're going to do two fractions multiplied by each other. So I'm going to split it. So 7 divided by 3.5 times 10 to the 24th times 10 to the 13th. And the only reason we can do that is because we have all multiplication in both the numerator and denominator. So now I can divide. What is 7 divided by 3.5? That one's pretty easy. It's just 2. And then 10 to the 24th divided by 10 to the 13th. When you divide two powers with the same base, you subtract those exponents. So 24 minus 13 is 11. So it's 2 times 10 to the 11. And that's already in scientific notation, so I do not have to adjust. Number 23 is another division. So again, I'm going to split this up into two different fractions being multiplied by each other. So 8.32 divided by 4 times 10 to the 30th divided by 10 to the 7th. Dividing powers with the same base is really easy. Our quotient rule says we subtract those exponents. My pencil's not working. So that'd be 30 minus 7, which is 23. So 10 to the 23rd. Then be careful here. 8.32 divided by 4. You got to be careful when you have digits to the right of the decimal. So let's go ahead and do some long division here. It won't take you too long. I promise I won't give you too hard of numbers. Divide by 4. 4 goes into 8 twice. Minus 8 is 0, and then put the decimal there, bring down the 3. 4 does not go into 3, so we put a 0 there, and then we bring down the 2, and 4 goes into 32 8 times. So subtract 32, that gives us 0, so we're done. So it's 2.08, not 2.8. So we get 2.08 times 10 to the 23rd. That is already between 1 and 10, so that's going to be our final answer. 2.08 times 10 to the 23rd. Moving on to number 24, multiplication. So we are going to reorder. So 2.34 times 3.2, so I can multiply their factors, times 10 to the third times 10 to the ninth, so multiply their powers. Powers are really easy to multiply together when you have the same base, so that'd be 10 to the 12th power. And then I'm going to go ahead and multiply 2.34 times 3.2, and I'm going to go ahead and put a 0 there. So the first lines are 0, so I'm going to ignore that line and start with the 0 here. 2 times 4 is 8, 2 times 3 is 6, and 2 times 2 is 4. Then that's 2 zeros. 3 times 4 is 12, carry the 1. 3 times 3 is 9, plus 1 is 10, carry the 1. And 3 times 2 is 6, plus 1 is 7. So 0, 8, 8, 4, 7. Since there are 4 digits to the right of the decimal, I need 4 digits to the right of the decimal here. So it's going to be 1, 2, 3, 4 right here. So 7.488, that's between 1 and 10, so that's good. So our final answer is 7.488 times 10 to the 12th power. All right, number 25. John was asked to write 4.76 times 10 to the negative 12th in scientific notation. John says the number will be very big. Is John correct? Why or why not? Be specific and complete. So that's actually supposed to say standard notation, not scientific. So John says the number will be big. Is he correct? Why or why not? So you need to be specific and complete in your answer. So we know that John is incorrect because a negative exponent means that the number is going to be very small, because that means we're dividing by 10. So a negative exponent means we divide by 10. So the number will be small. So it would have had to be a positive exponent for it to be big. So I'm just going to be a little short and sweet there since this is a video. So you can add more to your answer than that. Okay, 26. The enrollment at the University of Michigan in the year 1950 was 2.7 times 10 to the 4th. In 2000, the year 2000, the enrollment was set 3.8 times 10 to the 4th. How many more students were enrolled at the University of Michigan in 2000 than 1950? Make sure to show your work and what operation you were doing. So please, please, please write what you're going to do at least. So we want to know how many more. So that means we're going to be doing subtraction. So how many more in 2000 than 1950? So we're going to do the enrollment in 2000, which is 3.8 times 10 to the 4th, minus the enrollment in 1950, which is 2.7 times 10 to the 4th. Since we have subtraction is our operation, we have to have a common power. But look, it's already a common power. Yay! So that means we don't have to do any adjusting. So we can just subtract 3.8 minus 2.7. So 8 minus 7 is 1. 3 minus 2 is 1, so it's 1.1. So 1.1 times 10 to the 4th. More students in 2000 than 1950. So that means their enrollment went up, which is always good. Okay, number 27. The weight of a honeybee is 1.2 times 10 to the negative 1 grams. If a hive of honeybees contains 2 times 10 to the 4th honeybees, how much does the swarm of bees weigh? Make sure to show your work and what operation you are doing. So the swarm of honeybees, so we're not including like how much the hive is, just the honeybees. How much would all of those honeybees weigh? So we're going to be doing multiplication because each of those 10 times 10 to the 4th honeybees weighs 1.2 times 10 to the negative 1 grams. So we're doing 1.2 times 10 to the negative 1 times 2 times 10 to the 4th. So this is multiplication. We do not need a common power. We can just rewrite. So 1.2 times 2 times 10 to the negative 1 times 10 to the 4th. We can easily multiply those powers with the same base by adding their exponents. And it's okay that one of them is negative. It doesn't make a difference. We still add them. So it's going to be 10 to the negative 1 plus 4, which is 3. So 10 to the 3rd. And 1.2 times 2, I hope you can do in your head, is 2.4. So 2.4 times 10 to the 3rd, and make sure you have your label, grams. That's how much all of that swarm of honeybees would weigh by themselves. Next page is more story problems. In 2012, the population of New York was about 2 times 10 to the 7th, and the population of Oregon was about 4.2 times 10 to the 7th. How many times as big of a population does Oregon have than New York? Again, make sure you show your work and what operation you're doing. So how many times as big? So it means we're going to be doing division. So is Oregon then New York? So we're going to do Oregon's population, which is 4.2 times 10 to the 7th, divided by New York's population, which is 2 times 10 to the 7th. So since this is division, we do not need a common power. We're just going to split it up into 2 fractions. So 4.2 divided by 2 times 10 to the 7th divided by 10 to the 7th. So it's easy to do the powers. The quotient rule says when you divide powers of the same base, you subtract their exponents. So that's 10 to the 0 times 4.2 divided by 2 is 2.1. Now look at this. 10 to the 0. Anything to the 0 power is equal to 1. So this is just 2.1 times 1, or just 2.1. Another way you could have known that is any number divided by itself. Since this is a number divided by itself, that's equal to 1. So Oregon's population, I'm going to abbreviate here, was about 2.1 times as much as New York's. You don't abbreviate, I'm doing it to go quicker in the video. Okay, number 29, the average human heart beats 1.5 times 10 to the 5th times per day. The average month contains 3 times 10 to the 1st days. How many times does the heart beat in an average month? Make sure to show your work and what operation you're doing. So, since this many times per day and this many days, each day it beats this many times, so we're going to be doing multiplication. So we're going to do 1.5 times 10 to the 5th times 3 times 10 to the 1st. So again, since it's multiplication, I do not need a common power, and I can rewrite and multiply their factors together times their powers of 10. So 1.5 times 3 is 4.5. You can do that on paper if you can't do it in your head. Times 10 to the 5th times 10 to the 1st is 10 to the 6th. So it's going to be 4.5 times 10 to the 6th beats per month. And that's on average because we know that not every month has 30 days. Number 30. There are about 1.4 times 10 to the 8th pet fish and about 9.4 times 10 to the 7th pet reptiles in the United States. About how many more, underline that, how many more pet fish are there than pet reptiles? So how many more means we're doing subtraction. So there are more pet fish than reptiles. So we're going to do pet fish population minus pet reptile population. So we're subtracting, so we need a common power of 10. This time it does not already have a common power of 10.
So we're going to adjust the smaller one to be bigger. So I'm going to make this 10 to the 8th. And since I made that bigger, I need to turn around and make this one smaller. So it's going to be 0.94 times 10 to the 8th. That's the same thing as 9.4 times 10 to the 7th.
Now that they have a common power of 10, I can subtract their factors. So I'm going to do 1.4 minus, you've got to line up the decimals. I'm going to go ahead and put a 0 there to help me, 0.94, and put another 0 here. So I've got to borrow, so 10 minus 4 is 6. I got to borrow again. 13 minus 9 is 4, and then bring down your decimal. So I get 0.46 times 10 to the 8th, and that's my answer, but it's not in scientific notation, so I need to adjust. So now, since I'm moving it to the right, I'm making that number bigger, so I need to turn around and make this actually smaller. So it would be 4.6 times 10 to the 7th. So there's that many more pet fish than pet reptiles in the U.S. Last story problem here. Light travels 9.6 times 10 to the 15th meters in a year. There are about 3.2 times 10 to the 7th seconds in a year. How far does light travel per second? So we need to do division because we want
How far? So that's distance in meters divided by time. So light travels 9.6 times 10 to the 15th meters in 3.2 times 10 to the 7 seconds. So we're going to divide.
And remember, with division, we do not need a common power. We're just going to divide the factors and times that by the quotient of the powers of 10. So quotient rule says when you have two bases with the same power and you're dividing, subtract their exponents. So that would be 10 to the 8th. And 9.6 divided by 3.2. If you can't do that in your head, do it on paper, but it is 3. So it's going to be 3 times 10 to the 8th meters per second. That's how far light travels in a second. All right, the last part here is actually a reassessment learning target. So this is learning target 6 you're going to be reassessed on, which is ordering irrational and rational numbers. Now, these numbers are all rational, but they are in scientific notation or standard notation. So your final answer, remember, has to have the given numbers.
So you can convert any of the numbers that you want, but you shouldn't have to do that. And scientific notation's actually more useful here. So try not to take the numbers out of scientific notation. Rather, probably put some that are in standard notation into scientific notation.
Number 32, they're actually all in scientific notation. So to determine which numbers are bigger in scientific notation, you look at their powers first. So I've got -3, -3, and +2. So I have two powers that are the same. So I need to investigate those further. But since these are both -3 and this is 2, I know that this one's the biggest because it's got a positive exponent. These two are negative, and 2 is bigger than both these numbers. So this will be my last one. Now I need to compare these two. Since they have the same power of 10, I just need to compare their factors. So which one's bigger? 2.7 is smaller than 4.3. So since they have the same power of 10, that means that the smaller of the two is the 2.7 times 10 to the -3. So that's our smallest number. 2.7 times 10 to the -3. Then 4.3 times 10 to the -3. Then 1.8 times 10 to the second. And that's from least to greatest. These are all supposed to be from least to greatest. So you've got to look at their exponents first. The next one, we have two numbers in scientific notation, but the third one is not. So let's go ahead and put it in scientific notation. 1, 2. So 8.2 times 10, I moved it twice. It's a small number, so it's actually a negative exponent. So now I can see I've got an exponent of -1, -2, and -2. So again, these two I need to investigate further. But 10 to the -1, I can easily compare it to both of these numbers. Remember, the bigger the exponent, the bigger the number. -1 is bigger than -2 and -2. So this is going to be our biggest number. So that goes last. Now we need to compare these two and see which one's the smallest of the two, because that one will go first. So since they have the same exponent, we can just compare their factors. So 6.2 is less than 8.2. So that means that 6.2 times 10 to the -2 is less than 0.082, or 8.2 times 10 to the -2. So our smallest number is 6.2 times 10 to the -2. Then we have to write the given number. So 0.082. Then our biggest number, 5.9 times 10 to the -1. Now really, if you wanted to, you could put all these in standard form, but that's a lot more work. But you could. Next one. 420,000 is written in standard form, so I'm going to go ahead and put that in scientific notation. Here's your decimal all the way to the right because it's a whole number. 1, 2, 3, 4, 5. So 4.2 times 10 to the +5 because it was a big number. Now I can compare their exponents. Again, look, 4 to the 5th, 4 to the 5th. We have two numbers with the same exponent, but we can easily compare them both to this one since the exponent is different. 4 is the smallest, is smaller than 5, so that's going to be smaller than the other two numbers. So our first number is 6.2 times 10 to the 4th. Now we need to compare these two numbers with the same power of 10. So compare their factors. 4.2 is less than 8.1, so that means that 4.2 times 10 to the 5th is less than 8.1 times 10 to the 5th. So then comes next is, we got to write in the given form, so 420,000. Then 8.1 times 10 to the 5th. Last one. We've got one number in standard notation, so I'm going to go ahead and put it in scientific notation. Actually, we don't need to, because if we look at the number, these both have positive exponents, and they're the same exponent, so we'll need to investigate them further. But this one is a very small number, so if I wrote that in scientific notation, it would have a negative exponent. So I know this is going to be smaller than both of these. Or because you know that these have positive exponents, you know these numbers are going to be really big. And this one's small, so this one is the smallest. So I'm going to go ahead and write that one first. 0.00098 is our smallest. Now to compare these two, since they have the same exponent, I compare their factors. 3.2 is smaller than 9.2. So 3.2 times 10 to the 5th is smaller than 9.2 times 10 to the 5th. So next is 3.2 times 10 to the 5th, and last is 9.2 times 10 to the 5th. And that's your final answer. Okay, that's it for this video key. Thanks for watching, and let me know if you have any questions and study for your test. Thanks.